Good morning, everybody. You're in the right place. You're joining the MSIG webinar given by Axus Technology today, and we'll just wait a minute as everybody joins the webinar. Okay, good morning. I'm Paul Carey, Director of MSIG, and you are here to hear Axus Technology discuss how they contribute to advanced silicon carbide processing to enable future technology in all sorts of areas: AI, MEMS, sensors, automotive, and the semiconductor industry. We have Catherine Bullock, the Director of Process Technology, and Dan Trojan, the CEO of Axus, with us today. And for those who have seen our webinars in the past, I'm really going to quickly go over what MSIG does. And here's the quick agenda. I'm going to do an intro, and then I'll hand off to Catherine and Dan. And at the end, I'll come back and just with a couple of slides, and you guys just put on your seat belts and be prepared to learn more about silicon carbide technology than you knew before this hour. So very quickly, I'm Paul Carey, as I said, and MSIG is part of the Semi Trade Association. We are all about supporting the semiconductor industry. We have over 3,000 member companies, and we like to say we are your gateway to the semiconductor supply chain, which is actually, as you know, a very important thing these days. So the MEMS and Sensors Industry Group is a technology community within this big global semi organization. We are also global, and we have around 200 member companies that are focused on the sensor supply chain. And what we do is we do education and networking, and you can see that that means conferences and events. We have promotional opportunities, blogs, a webinar. This is an example of that. We also have work groups that solve industry problems to enable companies to sell their products and lower the barrier to selling their products. All of our companies are advanced technology, and sometimes you need to lower that barrier. We also have something that is very unique in this type of thing, is we have R&D funding. So we get money from the US government, and we fund advanced technology in positioning, navigation, and timing sensor technology. And we also do a little bit of biz dev, where we bring our member companies maybe to areas that they didn't know before, burgeoning markets, things that are predicted to grow a lot in the future. So we've been doing smart cities, and we're looking at the food industry, sensors in those areas. And so, yeah, we're at the center of the whole ecosystem related to sensors. Here's some of the companies. You might know some of these companies. There's some big ones, some smaller companies. Of course, Axus is part of this, and we have over 150 more companies. Very quickly, this is busy. I just want to show this to show that we're busy all year. We have a governing council. We have R&D funding. We do a lot of engagement, newsletters, webinars. We have monthly work group meetings. We even have a happy hour, and we send some lucky people a gift certificate to Uber Eats, and we all discuss what's going on in the industry. And of course, Semi is all about semicon events. Those are on the bottom here, but MSIG also does a lot of other things. And actually, there's one on here. Is it there? Sensors Converge. We were just at Sensors Converge this week. We had a session on Monday. It was a great session. A lot of MEMS and Sensors people got together. Our next big events are coming up. Semicon West. And if you put your QR, you hold your phone up here, this actually will give you a one-day pass for free. And our big day is Wednesday of Semicon West. So get a one-day free pass, show up, go to the reception at the end of the day. We have MSIG on stage. It's going to be a great day there. One more thing, the MEMS and Sensors Executive Congress is only 15 weeks away, and I can't stress this enough. This is where you want to go if you're an executive in the MEMS and Sensors industry. Oh, I didn't mean to do that. And this will also get you to the registration there. Very quickly, our R&D funding. Many of you already know what we do, but it's positioning, navigation, and timing R&D technology. Where are you? Where are you going? And when are you there? We've been doing this for over 4 years. We had a phase 1 that's done. We have a phase 2 that's a 5-year program. We have done the first year, the second year is beginning, and the third year starts in a month. So if you're interested in knowing more about how to get R&D funding from MSIG, this QR code will lead you to a website, and you can put your email in. Some of the things we're funding: inertial sensors, IMUs, accelerometers, gyroscopes, quantum sensors, atomic clocks. It's all great stuff. And these are the companies that we funded in the past. Some of them you know, some of them are a little bit smaller. There's a couple of universities. So yes, universities are invited. And so we look forward to interacting with you on this and picking our third year. All right, back to today's webinar. We have a great, I'm very interested in silicon carbide technology. Everybody knows about silicon, everybody knows about carbon. When you join the two, you have this wonderful substrate. And Catherine Bullock and Dan Trojan, who have been in the industry for a couple of years, they know a few things about what's going on. They know about the technology that they're going to describe. And so I'm going to hand it off to them and let them tell you how Axus Technology can enable some very interesting things that are going on in the semiconductor world these days. And I'll join you at the end. Okay, so take it away, Catherine and Dan.
Hi, everybody. I'm Dan Trojan, CEO, founder of Axus Technology. A little bit of my background is I've been doing CMP since I first started working with IBM in the late 1980s, believe it or not. So I've been doing CMP for coming up on my 40th year. We started this company, Axus Technology, was formed in early 2002, and the business model was fairly straightforward. It was to take all the experience that we had collected in our OEM, equipment development, process technology development experience, and at first bring that into the secondary market, where we're developing proprietary upgrades for existing legacy equipment to extend its life cycle and its application space. And then in 2017, 2018 timeframe, we saw the need for what is really in the 200 millimeter space, is to really bring to the market advanced CMP technology for 200 millimeter diameter and smaller wafers. We do a lot of that work in our foundry, where our applications, where we do a lot of leading edge development work. That activity is run by Catherine. By focusing in that area, we saw that there was a really important need to bring advanced technology to the 200 millimeter and smaller part of the market, wafer size, and a big part of that is advanced materials, evolving new applications, and certainly compound semiconductors, and more specifically silicon carbide, is a very big part of that part of the market in the industry, and something where we focus extensively on. So we brought a new state-of-the-art 200 millimeter platform to the market in 2020. We call that product Capstone. And the timing of bringing that to the market really coincided almost perfectly with the sort of the knee in the curve of the expansion of compound semiconductors and silicon carbide, specifically for really the electrification of our society. So we've done a lot of advanced technology development around compound semiconductors, silicon carbide, and GaN particularly. And so that's what we're going to be talking about more today, and I appreciate everybody's time. Thanks. Catherine?
Oh, great. So I'm Catherine Bullock, and as Dan was kind enough to say, I run the foundry and the lab services and the process development division for Axus. And man, we get to see some really great projects come through. We get to see all the advanced materials and really help people with a lot of projects to get these new materials flushed out and see what's really going to work and go forward and what's not, and really help people with their initial device design and up through some initial processing of these. And man, it's just an exciting place to be, and I'm so happy about it. And I've been doing CMP for about 27 years, in the industry almost 30 for various things, and CMP has been the common thread through all of the technology that I've picked up over the years. So yeah, I'm just really happy to be here and be able to talk to you guys today. So.
Okay, thanks, Catherine. So just a little bit more about our company. We're very proud of the fact that we have collectively, it's now, well over, I would say over 400 years of combined CMP experience, and that's all technology-based CMP experience. So that is process engineering, hardware design engineering, software engineering, mechanical, of course, field service and whatnot. So it is a company, we're not the 800-pound gorilla in the industry, but we have collectively, deep, broad technical experience in CMP that I think surpasses any company in our industry at any scale. And our focus is really bringing, and our strength, I would say, is innovation. So, and we'll talk more about this today, about silicon carbide being so different, and the level and pace of integration that it demands. But that's something we do. We're what some of our customers refer to as a right-size company. We have a worldwide presence, but we're also able to, test and learn and innovate and productize, as a result of that effort. And we could do that at a pace we're nimble enough and fast enough and efficient enough that we can do that at a pace that's very well fits with and supports the needs of our customers, because we understand that how important that is. Next slide, please. Talk a little bit about our footprint here. We're a global company. I'm sitting here talking to you today from Chandler, Arizona, which is our headquarters. We have 2 operations in Chandler. One is where we do all of our engineering, manufacturing, customer support, supply chain management. That's 65,000 square foot facility here in Chandler. And then just down the street behind me is a 25,000 square foot facility, which houses all of our clean room and all of our support personnel and resources for all of our clean room activities. Hercules, California is a service depot that's located in Northern California, where a lot of our customers are based. And then we have representation from reps and distributors throughout the UK, Central Europe, Southern Europe. We also have distribution in the Middle East area, Israel, as well as covering, pretty much all of Southeast Asia. That's Korea, Japan, Taiwan, Vietnam, and we're not presently in the market in China. Maybe stay tuned on that for the future. But we do have a worldwide footprint and support network, because our customers, of course, are based around the world. Next slide, please. So this is the agenda, general agenda we put together here. I think it's pretty straightforward and self-explanatory. There's a lot of exciting developments that are going on in the industry right now, and we'll talk about these drivers, but AI, electric vehicles, renewable energy, efficient distribution of energy, and efficient use of energy is what's driving a lot of this. And silicon carbide is a very interesting, unique material. We won't go into a lot of details on that here, but it does present a lot of new opportunities, but certainly a lot of challenges that go along with that. And we will be covering some of that in some detail here today. With that, in terms of getting more to the technology, the technical aspects of the topic, Catherine, I'll hand it over to you.
Great. Okay, next slide, please. All right, so man, silicon carbide and GaN and other compound semiconductors has been such a hot topic for a couple of years now, and really, why is the change is, I guess, the topic of today, and how are we helping with that? Because silicon substrates and silicon material and base devices have been the gold standard for, oh my gosh, probably since the 50s, right? So why are we now all of a sudden changing? And I guess that's a big question for a lot of people, because it's a significant change, and we have to change over a lot of what we're doing and a lot of thinking, and far as just device manufacturing. So there has to be a really compelling reason to switch over to these materials. And we have done a lot of research probably over the last, it's probably been concentrated in the last decade. Would you agree, Dan? Probably on some of these materials. And we've really, as an industry, kind of settled on silicon carbide being the next gold standard for a lot of these power devices, things for, and because it supports all of the industries for electric vehicles, and the data centers are such a big part of this. I mean, the data centers alone, for all of the sensors and the AI and the things that we're using day to day, I think they're using probably 2 to 3% of the world's power supply just on holding our data. And 40% of that usage is just on keeping the data centers cool enough to run on silicon-based devices. Now, we can change a lot of that by using silicon carbide devices, because they run at a much different temperature. They can handle higher temperatures and higher power. And, so it's just a really good overall material to drive a lot of these initiatives that we really need to focus on in the world. And we can take that onus on as an industry and really help out a lot of items. Yeah, I think that's the next slide.
One thing I'd like to add to that is just that if you think about AI and data centers specifically, and there's articles in the media you can read about this, but they already consume so much power that they talk about just the amount of power, electrical power, that an AI type of data center where you got these, very high-end processors running at very high, cycle speeds, consuming so much power that they talk about data centers actually consuming the amount of power some, say mid-sized countries consume. So you've got this huge demand for AI now, which drives a huge demand for data center processing scale and bandwidth. And these things consume so much power to bring into those data centers for that functionality. And then on top of that, you've got to be able to generate that power. You have to be able to transmit it efficiently. And then and these things generate an amount of heat. So you have to then generate much more power to withdraw that heat from the data center. If you can do all that with 30 to 50% more efficiency, let's say with something like silicon carbide and GaN, think of the additive effects of generating that power more efficiently, transmitting that power more efficiently, being able to operate those devices at higher temperatures, therefore requiring less cooling, and that cooling also being able to do much more efficiently. So the additive effects of what is enabled by these advanced compound semiconductors, when you think about it, is really quite amazing and critical for our future.
Critical, absolutely. Yeah, next slide, please. Yeah, and this kind of ties in right to this slide here, right? It's the continuation of what we've been talking about. So the silicon carbide devices are much smaller, and they're much more efficient for all of this power transmission that Dan mentioned. So we don't need the big in-device heat sinks with copper and some of these aluminums and some of these other materials. So we can really more efficiently use those precious materials in other devices, but we can maintain and increase that power efficiency with these silicon carbide devices. There's another benefit, is that what we can create out of them with better efficiency is smaller and lighter. So that really plays into the electric vehicle market, where we don't need as many batteries and we don't need them to be as heavy. So the charging is faster, and we can go a longer distance with those electric vehicles on the same amount of charge, and just really just use that power more efficiently. So did you have any other thoughts on that one, Dan?
No, carry on. Thank you.
All right.
All said.
Great. Okay. Yeah, next slide. So we've talked a little bit about some of the benefits of silicon carbide and some of the other compound semiconductors, because we do need to talk about those as well in conjunction with silicon carbide. I think we're going to see the technologies merge a little bit. I know there's some debate right now on silicon carbide or GaN, but I really can see a future where we're going to combine the two of them and really use the best of both materials to make these really, really interesting next devices. So we can use GaN for higher switching speed. We can use the silicon carbide for better power efficiency. And it's just going to be really interesting to watch what the really smart people with all the device designs and the way that they package them and put them in consumer electronics and things like that, of what's going to happen over the next few years. Okay, next slide.
Exactly. I would maybe emphasize the one bullet there, which is reduction in cost. We're very focused on these materials, specifically in the CMP space, and you know, it's silicon carbide. Processing it is relatively expensive, and CMP is a portion of that, you know, cost of ownership for the material processing. And so people have asked me from time to time, we talk about bringing down the cost in order to increase the adoption of these new materials, which is already happening at a very fast pace. But and they ask me, we talk about cost reduction, but is there anything happening there that is real, it's tangible? And I would definitely, my response is always yes, absolutely. I mean, we've done things, a lot of innovation, a lot of new technology development and IP around that, to really drive down the cost of our process space, and that will continue, and that will also drive more adoption. I think Catherine's going to talk a little bit more about that, but this reduction in cost that we're talking about in our small part of the whole equation here is real, and it's happening as we speak, and it's quite significant.
Mm-hmm. Yeah, I agree.
Thank you.
Thanks. Yeah, next slide. So yeah, with these materials come some new challenges, and we've got a whole suite of really smart people in this industry that are taking on that challenge, because we definitely need to. With silicon carbide specifically, we have to have the requirements for that are so much more stringent than what we were using for silicon-based devices. So the crystal growth has to be perfect. When we are finished with it, the surface finish has to be perfect all the way to the edge. And that's how we're getting all of these smaller, high yield, just really excellent devices out of this. And the onus is really on us to make these better materials and these better processing. For us specifically, it requires some pretty aggressive conditions. This material is nearly inert. And so we need to really up our game as far as those process conditions. The process temperature is much higher, so we need to learn how to manage that. We're working very closely with the entire ecosystem for CMP to look at different processing chemistries and different consumables, because we're just driving an entire industry here to make these new devices. They're transparent, which is because just is a new kind of challenge for certain machinery and sensors and things like that. So we need sensors that are more advanced than what we were using for silicon processing to be able to make new devices. So it's kind of this whole ecosystem. So we're really trying to shift our mindset into these new materials and come up with some really creative solutions.
Yeah, and again, a couple of points to add here. One of them is that you know, because silicon carbide is hard, it's the second hardest material in our world, next to diamond. And so we have to polish at very high speeds and pressures to get a reasonable removal rate to keep that cost down, the processing time and cost down, and the throughput and the productivity of the equipment high as possible. And also, so it's a very different paradigm than traditional CMP in that sense, where temperature was not so much of a concern, even though it's a very critical variable. And also there's other things. We have to polish both sides of the wafer as an example. So there was you know, traditionally we went from CMP, and I've been doing it for 40 years, Catherine, almost as long. You know, we first started out with silicon surface polishing, and then we went to oxide, you know, dielectric layers for interconnect planarization, and then we went to tungsten CMP as a better alternative than what was a dry etch back process. But we went from, you know, so silicon to oxide to tungsten to copper, and now different barrier materials and whatnot. But when we did that, the equipment requirements were always pretty much the same. The process conditions were pretty much the same. It was mostly changing to an optimized consumable set for different materials, but everything else was pretty much static. All of that, then that was our expectations. Us veterans had the same expectations when we then evolved to silicon carbide and other compound semi materials. But the reality is, particularly for silicon carbide, is it's a whole new clean sheet of paper requirement. It's just that much different. And so the point was made very well last year. We had a silicon carbide sort of symposium at SemiCon West. It was a mixture of both suppliers as well as end user customers. Catherine presented at that event, and one of the messages that came through loud and clear from the customer community is, please don't try to force fit a traditional semiconductor silicon traditional application, say silicon CMOS. Please don't try to do a force fit of that equipment design and capability and functionality for something that's as differentiated as silicon carbide, because it's not approach is not working well for the customer community. We heard that loud and clear. We were already well positioned to accept that challenge and execute on that. But it's an important thing to keep in mind, because these materials are so different. A lot of the conventional wisdom and tribal knowledge that existed from traditional silicon CMOS processing really does not apply to much extent for silicon carbide. So I just want to interject that for the people that are listening that may want to understand how this all fits together, or where things do and don't fit together.
Yeah, it's a good point. And you're absolutely right. I mean, these materials are requiring us to flip everything we knew on our head and rethink just about every piece of the equipment and the equation as far as processing these materials, and looking forward to the quantities that we need and the quality that we need. So yeah, I think that's really imperative. And it's really come down, like Dan said, is that the equipment manufacturers are now really needing to be involved in the end requirements of the material. You can't just give off a one-off standard machine and expect it to work for these new materials. So that's really what we've concentrated on, is really understanding that end goal and designing equipment to be just the right fit for these new materials.
Exactly.
Great. Next slide. So, and it's not just CMP, right? So there's a lot of new equipment being developed and a lot of new material things being developed as far as being able to make and just get to a substrate that we can then use for silicon carbide devices. So at first, the silicon carbide puck is grown in a very high temperature furnace. This isn't the same way that we grew silicon substrates. It requires a lot of energy and a lot of heat to grow those. And the pucks that come out are relatively small compared to what the big silicon ingots were. So that's its own ecosystem of technology that's being developed. And then those pucks are sawn with different kinds of materials. There's some development equipment-wise going into new diamond wires, or laser splitting of the pucks into rough wafers. And so that's a whole new technology that's having to be redone, in my opinion. And so we're seeing a lot of advances in that forward, into CMP technology. Then we end up shaping the wafers. So we do an edge bevel on these and do a rough lapping. Maybe some people are starting to skip that step. And that gets us to a rough wafer that we can then get into what Dan and I's zone is wafer grind and CMP. So there's quite a bit of development that's happening even before the wafers get to us for that final finish. And then the CMP specifically, oh gosh, I think Dan and I could probably give a university lecture on CMP at this point in time. But, so that's a really challenging part of this ecosystem, is just CMP is inherently kind of difficult. There's so many factors that go into it. And the requirements for us are, sub-angstrom roughness. It has to be perfect across the surface. We're seeing the differences in the crystal growth. We uncover issues for people in those, and the wire sawing. So we're really having to work with multiple layers of this industry to create something that is just a perfect silicon carbide wafer. And then once we have that done, then the wafers are ready for an epitaxy layer if that's what the device requires. And then we can move on. But as far as what CMP does is it sets up a perfect surface for then perfect devices that we need for all of these industries. So any other thoughts, Dan, on that one before we move?
No, please continue. Thank you.
All right. So let's go to the next slide. So as Dan's alluded to, and I have too, there's been some issues with the cookie cutter processing equipment that's been out in the industry. The silicon, because the pucks are grown so differently and slung so differently, and there's different requirements. The silicon carbide material specifically has to be very thin compared to the silicon processing that we've had to use before. So we've really had to rethink just basic machine handling of this material because it is so thin. I mean, you can almost set it on a clean room table and watch it bow and flex, which is a little bit scary for traditional machine applications. They can also, it's very, as hard as it is, there's also a lot of opportunities for defectivity. So we have to look at all the touch points in the systems, machine handling. If we can do it around the edge, that's much better. The temperature degradation, the temperature that this process creates really degrades a lot of the traditional equipment material. So we've really had to up that and really learn how to manage all of that heat through this. So those one-size-fits-all machines that we've used all in the past that we know and we love are just not able to keep up with the new demands. And we're having to drive down cost of ownership because the traditional equipment is really pretty high, especially in CMP. The traditional equipment uses so much water, and that's something that we know is a precious resource, and we're trying to work to really reduce that in CMP. We've got to look at new fault detection and data collection because we need to be able to run these so fast with so much data, especially as we look towards electric vehicles. There's going to be requirements in maintaining all of those records for every wafer that we polish. And I think we just are in a good spot to change a lot of these drawbacks from the traditional CMP tools. So I'm sure you have thoughts on that one, Dan.
Yeah, well, just add that a little bit. I mean, one of the things is we talk about, environmental sustainability. I mean, one of the things about just being a state-of-the-art tool is if you look at things like electrical power consumption, water consumption, waste stream volumes, all this type of thing, efficiency of consumables usage and that type of thing. Mm-hmm. When you go to these just a state-of-the-art tool like Capstone, I mean, a lot of those things just are inherent in that. We consume a fraction of the power. We use an order of magnitude less water consumption. So for customers in our industry is very focused on sustainability and environmental footprint and whatnot. So, those are all areas that are maybe not front and center and visible and tangible, but those things are happening as well. Fault detection and data collection. SEMI has done a lot of development work. We have what we call now interface A, interface B, interface C. So we traditionally had just host to process tool communication for managing material flow through the fab, reporting exceptions, events, that type of thing. But SEMI as an industry realized that there's so much more data that if we could capture that data, collect it, and make it available to the customer, to the end users, they could use that information very effectively and very intelligently. And so again, for these advanced standards, which we support, and a lot of the legacy CMP tools do not. I mean, especially for something like a new application and a very challenging application, new material, very different process and requirements, having all this data collection ability and ability to collect that data and analyze it and whatnot is very important as well. So these are some of the things that, when we say we come out with a new tool, maybe in our industry every 20 to 25 years, that's all the additional benefits that come along with that. And that's something I think that benefits our customers significantly as well.
Yeah, those are all really great points. And I think we're at next slide, please. All right, Dan.
Okay, I'll jump in here and I'll talk a little bit about the equipment itself. So you see an image there of a Capstone tool. We'll go to a lot of the details. I'll just keep this at a fairly high level, specifically for silicon carbide. And as I said before, silicon carbide is a completely different animal. To take a legacy CMP tool and try to make that work well it's very difficult. So we designed the capstone. I was actually the architect of the developer of the architecture. It's designed to be a very high throughput platform with a very small footprint, but have absolutely state-of-the-art process capabilities. We talk about a bridge tool. So capstone architecture is unique in the sense that you can run all one size, of course, but you can run two different sizes side by side. And so what's happening in silicon carbide is it went from 100 millimeter to 150 millimeter, which is probably 90% of the material right now is 150 millimeter wafer size. And a big challenge for end user customers is to scale the growth of the material to a 200 millimeter diameter, because it's a very challenging material to make, as Catherine alluded to earlier. So the customers are looking at this primarily 150 now, and then transitioning to 200 millimeter in the near future. And so with all the challenges with the process, and a lot of those have to do with process conditions, consumables, selections, and things like that. But with capstone, you could be running 150 millimeter today, and then when you're ready to start transitioning to 200 millimeter, you can convert half the tool to 200 millimeter. Now you can run 150 as you know, or 200 millimeter interchangeably without any hardware software changes, and you could actually run those two wafer sizes simultaneously. So you could literally be processing a 150 and a 200 millimeter silicon carbide wafer on the same set of consumables at the same time and at exactly the same conditions. And so a lot of the variables that you would normally have to sort of partition to get through that transition, you can eliminate 90% of those variables, let's say, because the fact that you can run these two different materials at two different sizes in exactly the same conditions at the same time. Environmental sustainability, we talked about it earlier, that kind of goes hand in hand with just being a state-of-the-art technology in terms of control systems and power efficiency and things like that. The next one here is process temperature control. I'm going to go quickly to try to get through this without taking too much time, but because we run silicon carbide at such high speeds and pressures, we generate a lot of heat. And if that heat is unchecked, then we'll basically reach the upper temperature limit. First, what happens is you reach the upper temperature limit of the polish pad itself. And when that starts to harden and melt, bad things happen very quickly. So, or if you want to avoid those limitations, now you have to run at less aggressive conditions, lower speeds and pressures, to keep the temperature low enough to not cause that catastrophic event. And when you do that, you're using your polish times are longer, so your throughput is less. Your slurry consumption is more because of the polish time being longer. CMP slurry for silicon carbide is the most expensive CMP consumable in the process, and the costs are significant there. So what we developed is what we call process temperature control. It's a patented technology where we can control the temperature of the CMP process through the recipe, a setting in the recipe in real time. We can't go into the details here today, but basically what you do is you just set this. And so let's say your upper pad temperature is maybe 60 degrees C as typical. So we can set a set point in a recipe of 55 C. We can run under very aggressive process conditions and maintain that temperature set point for indefinitely. It's very important for silicon carbide for cost of ownership, throughput, process quality. It actually has a lot of benefits for non-silicon carbide CMP applications, but that's outside of today's discussion. But very important technology. Carrier technology is important because we want to have the prime quality of the surface quality, the wafer flatness, and it being able to handle these very thin, fragile wafers, all of which Catherine alluded to earlier, requires different thinking in terms of carrier technology, which we're also very focused on. Fault detection, we talked about the other benefits of the state-of-the-art control system. Another nice thing is Capstone is the only tool in the marketplace that has both integrated polishing and cleaning integrated together. Ideally, what you want is you want to have clean wafers in and clean wafers coming back out of the system, all with a minimal number of handling steps. And so Capstone has a fully integrated double-sided brush scrubber. with chemistry and megasonics and whatnot to get the wafers to an epi-ready state of cleanliness, and all integrated in one system. Again, that's unique in the market today. Integrated metrology, we have a wide suite of options where you can have, this can go into conjunction with closed loop control, where we can measure wafer on board to capstone. We can measure certain properties of that, process the wafer, measure it again, understand what the differences were before and after CMP, and then with our closed loop control technology, we can automatically make changes to the process recipe for subsequent wafers on the fly. So you get very tight control of all the critical, on wafer metrics in terms of shape or uniformity, or material removal amounts and things like that. And then we talked also about surface roughness being a critical parameter for an epi-ready surface, and we're, in that sub-action range, as Catherine mentioned earlier. So very, very good functionality there as well.
Okay.
Next. Anything else, Catherine, to add?
Oh, I would just say I think that's really what makes you and I successful in this space, is that, I come at it from the process and the end user and the device side, and you come at it from the equipment side. And we've really worked closely together with this amazing team that we have to really respond to the needs of the market and all these new materials that are coming out. So we can innovate so quickly this way and really come to enable everybody else's goals of high volume, inexpensive manufacturing for these new materials. So that really is what drives us, or at least I think that's what drives me. And so it's just been a dream to be able to create these machines and see so many people be successful because of what we can create so quickly.
Very good, thanks.
All right, excellent.
Next slide, please. This is, we talk about just sort of putting a time dimension to this. This is a roadmap, our roadmap that I'll go over here quickly, but I won't go back to the founding of the company, but we talked about some of the general product developments we've done here. But if you look at the removal rates here for silicon carbide process, 4 to 5 microns per hour is about where we started when silicon carbide processing, or adoption really started to take off. We show it here, the process temperature control, capstone, all in the 2020 time frame. But you can see here the steady progression of increases in removal rates, 4 to 5 to 6 to 7, and now we're up in the double-digit removal rates, with still quite a room to go on that as well. So these are just sort of examples of what we talked about in terms of this ongoing technology development that silicon carbide requires, and the pace at which we have been able to drive that innovation and bring new products to the market. So again, being a right-sized company, I think, is important, because it would be, the scale is important in terms of how quickly a company can do this type of development and innovation, and I think we are very much leading the field in that respect. Another thing that to point out here on the timeline here is something that we're very focused on right now is slurry reclaim. So slurry is a very expensive part of the overall cost of ownership for silicon carbide CMP, and for reasons due to the sort of unique characteristics of slurries that are new and unique for silicon carbide CMP, as well as the properties of the material itself and other things, functionality that we've designed into the equipment. We're now at the first time, slurry reclaim is always, because of its cost, has always been sort of the holy grail for CMP in our industry, but it's a very difficult thing to implement effectively. And so, but we are, with the testing we've been doing, the work we're doing, we see a pretty clear path to being able to make that also sort of a standard benefit for silicon carbide CMP, and from a cost of ownership standpoint, environmental standpoint, and whatnot, that will be a huge new paradigm for us in this space. And I think it's really something for people to be aware of and keep in mind going forward.
Great.
Next slide, please. So to wrap things up here, particularly for silicon carbide CMP and other compound semiconductor materials, there will continue to come along in new applications. We haven't talked much about micro LED and advanced packaging and whatnot, but these all fall into that same general category of new opportunities and technologies in our industry. For silicon carbide specifically, we do believe we are leading the way, and we'll continue to innovate and support our customers at the pace we have. And I think it's a very exciting time for us to be in our industry, because all these new materials now that are coming along, and all the benefits and solutions that they offer to society in general, and quality of life and whatnot. I think it's just a very exciting time and space that we're proud to be part of.
Great.
And I thank everyone for their time again, and I'll hand it back to you, Paul.
All right, now it's time. Thank you very much for that overview on the capstone and what it can do. And now it's time for questions. And there are some questions. Of course, if those who are on didn't see it, yes, these slides will be distributed. So don't worry about that. And there are a few people apparently whose IT departments blocked this, and this is recorded. So you can see this non-live. Okay, so I guess one of the questions you might have answered was, so silicon carbide CMP is done at elevated temperatures. Can you comment more on the temperature range that you use for doing this?
Well, oh, go ahead.
Go good.
Okay. So without the process temperature control, it is very, very easy to reach 60, 65. I think I've even seen 70 C on some of these polishes. And once you really get over about 60 C, the process absolutely shuts down. You reach the pads, and some of the slurries really start to break down over that. So we try to go and control down in the 50 C range, maybe 50 to 55 for most of the applications that we're seeing. We are seeing some people come out with cooler processes that fit their processing metrics and things like that in their factory for their devices. But anything over 60 C, and you really start to see a lot of breakdown.
And
Okay,
I'll
so
add to that. I'll add to that, Paul.
Okay, go ahead.
When we talk about temperature, there's a couple of things that we can measure that are important. One of them is the surface temperature of the pad, for the reasons we've talked about already. And it's very easy to get up to those limits where bad things happen quickly, as I said. But there also is an issue with the temperature of the wafer itself, and critical materials and components in the carrier that is applying the pressure and the speed to the wafer against the polish pad during CMP. So those things are more difficult to measure and control. But you can also get some phenomena where, like as an example, the surface temperature of the wafer itself gets so high that you actually start to sort of bake the byproduct of the process onto the surface of the wafer, much like maybe when you fry an egg, it sticks to the pan and it's difficult to remove. But so you get this baking onto the byproduct of the surface of the wafer, which does a couple of things. It makes it's impossible to clean off in post-CMP cleaning, but also it generates a very high friction between the surface of the wafer and the surface of the pad. And then you get this runaway condition where the temperature, the wafer temperature goes up. Now this stuff starts to stick to the surface of the wafer, drives more friction, more heat, and then you just get this runaway thermal condition. So there's a lot to that, but those are the sort of the fundamental principles.
Interesting. So the first takeaway I have, and maybe I'm not the only one on the webinar, is when you said you control the temperature, a lot of processes, as you make the temperature higher, they go faster. And so if you want a high throughput, I thought you were going to say, yeah, we do it, 150, 200 C. And what you're saying is, yeah, we control temperature, and it's in a range, and you don't want to get above a certain temperature because you have all sorts of problems.
That's exactly right.
So there's a bunch of questions along the same vein here is, okay, so you guys take wafers that have been cut out of a boule, and I think what people want to know is what's kind of the general starting thickness of a wafer, and then what do you end up, is there a range? I know it depends. Silicon carbide is part of the device, right? So it matters how thick the wafer is. So can you comment on the typical thicknesses, and then After that, how long does it take to get to that thickness typically?
Go ahead, Catherine.
Okay, all right. So we started seeing silicon carbide at 500 micron thickness. That was kind of the starting material that we were seeing several years ago. And those are really mechanical grade silicon carbide. And we really cut our teeth on those as far as some of the processing metrics go. And then we very quickly started seeing people adopt probably 300 to 350 micron is the pretty typical thickness right now for most 150 and 200 millimeter silicon carbide wafers that we're seeing. We're seeing some starting to look at material that's much thinner than that, which I won't comment on an exact number because, you know, that would be a bad idea. But most typically they're 300 to 350 microns right now. When the wafers get to us, as far as the grind and the CMP steps, we're looking at removing probably anywhere from a half micron per side up to maybe 3 or 4 microns per side. So really in total, we're taking off probably less than 10 microns for most people, you know, 2 to 10 microns. And we're really reshaping the wafers to correct for some of the wire saw issues that we're seeing, or maybe some of the crystal growth opportunities that we're seeing in the material itself. So that's a lot of what these advanced CMP tools that we're developing and concentrating on is really correcting the shape of those wafers so they're near perfect when they go to epi and then device production.
Yeah, I remember a long time ago in my double E class, when you wire saw a boule, you get kind of a triangle.
Yeah.
Because the wire saw gets thinner as you get through the boule. So you're saying you correct for that. So these wafers, when they show up in your capstone machine, again, you guys have an apps lab, so you can do it for companies there, but you sell the tool. So those wafers start out around 10 microns thick, and then you make them 3 to 500. Oh, wait, you take off 10 microns, right? Okay, so they start off around 3 to 500 microns thick, and you just take a little bit off. Is that right?
And that's enough to recorrect the shape, take a lot of the stress out of the wafers. So sometimes they come into us and they'll wobble on the table because they're under so much stress just from the material strain. And so we can really go through and relieve a lot of that stress and end up with a flat wafer that has the correct TTV when it's flat. And so that's something that people look towards us helping them do.
Yeah, and so there's some other sort of high level considerations here. One of them is when you slice the wafers from the boule, you know, like a wire saw, for example, can create quite a bit of damage in what we call kerf loss, right? The width of the wire that you're losing in that material. The material is very expensive currently. Costs are coming down, but so you want to maximize the yield from that boule. And one way to do that is to say go to more advanced technology like a laser splitting is something that's evolving now. We work closely with one of our key customers is Halo Industries that's doing a lot of exciting work in splitting off these wafers with a laser. So you minimize the kerf loss, you minimize the surface roughness of damage. And those are, you know, sort of economic considerations. How many wafers can we get out of a boule is a very important economic metric right now. And then you also look at another part of this, which is wanting to make those wafers thinner and thinner to improve the device performance. And that's very much along the lines of what, you know, has happened in our industry, say, over the last 20 years, where you look at like silicon on insulator technology, where you want to find creative ways to minimize the substrate, the thickness of the substrate. And now we're starting to work on these very same types of you know, objectives for silicon carbide as well. And I think that's a trend that's going to continue more or less kind of follow the way it did for SOI for silicon. But these are a lot of sort of new applications that are evolving around it, either for technical, you know, device performance reasons or economic reasons, and that's going to continue to drive a lot of innovation as well.
Yeah,
okay, I would be remiss. Sorry, we don't have that much time, but I would be remiss. There's a bunch of people asking, how long does it take to do this? To take these 10-ish microns off that starting wafer?
Well, initially you have to take these and you lap them, which is a slow process because, you know, it's probably, I don't know, that's pretty far upstream for us, but, you know, it's probably an hours long process to do that lapping and get those wafers to a condition where you can then grind both sides of the wafer using a back grinding machines. which we also support. And those processes are very slow. You can grind, typically you're removing, say, 50 microns per side of the material in grinding, and it's usually a two-step grind. It's coarse and then fine. Where you can grind a silicon material in, say, 5 microns per second, let's say, is a feed rate where you're grinding that material down. In the case of silicon carbide, it's typically, say, 0.1 or 0.2 microns per second. It's orders of magnitude slower. So these grind times, instead of being a minute, say, typically for a silicon wafer, are 30 minutes, or for a silicon carbide wafer. So very slow process.
And that's why we're driving those removal rates for silicon carbide up higher and higher, and that's why that's such a focus for us, is because it is very slow. And so us getting up to 12 microns an hour on a silicon side, and we're pushing that quite a bit higher with some innovations that we're not ready to reveal now. So yeah, so it takes a little bit to do this, and that's really a big driver.
If you look at removal rates for a silicon type of process, where it's microns per minute, and if you look at removal rates for silicon carbide, as we saw in our roadmap here, it's microns per hour. So again, well over an order of magnitude difference. So it's difficult material process.
Gallium nitride. You
Yes.
guys working on CMP for gallium nitride too?
Very much so.
Oh yeah. Oh yeah.
And what's the level of interest relative? Are silicon carbide and gallium nitride neck and neck, or which one has more interest right now, and where do you see that going?
I think a lot of the innovations happening is with silicon carbide substrates right now. Gallium nitride as a film and a material has been around for a long time, so I think that's a little bit more well understood. It has its own challenges of being a very brittle material, so some of the advancements that we're making in machine handling and what we're doing with the machines are going to be very well suited for when gallium nitride really ramps up, which I think is probably, we're right on the cusp of that right now. So I do see those pieces of the technology merging probably in another 2 or 3 years.
All right. There's so many. When you control the temperature, you have in situ diagnostics, right? Can you talk about how do you control the temperature of this process?
Probably not going to go into the details of how we do it. It's a very novel method that we developed and patented. And as far as how we measure the temperature, that's quite mature in CMP tools. We basically use a pyrometer or infrared, black body thermometer that can measure the surface temperature of the pad. And so we have that a standard feature on our tool, and we use that as the input source for us to close the loop on controlling the temperature in real time.
And then you mentioned you're going to recycle the slurry and lower the cost of ownership. Do you guys, who makes the slurry? I mean, just a little bit curious. This slurry is like a fancy sandpaper, right? So yeah, what's going on with that?
Well, I would say one thing that's very unique is for silicon carbide, the chemistry itself is quite unique. Most of them are potassium permanganate, some are sodium permanganate. So it's a very different type of slurry in chemistry. You talked about sandpaper. That's pretty simplification, but actually for silicon carbide slurries, a lot of these have actually very low abrasive content, and in some cases no abrasive content, which from a slurry management standpoint makes it a lot easier, and from a reclaim, recycle, reuse standpoint also makes it easier, because not having that critical component in the mixture of the abrasive really simplifies all that, significantly.
That's fascinating. Okay. Yeah, so I've learned a lot too. I always thought slurry meant it had a mechanical component, so it doesn't necessarily have that.
Yeah, so CMP, chemical, mechanical, right? So some are a lot more M and a lot less C, and others are a lot more C and a lot less M, and it's a wide spectrum, but it is quite a different situation with silicon carbide than it is for traditional other slurries for other CMP materials.
All right, I think we are 1 minute from the top of the hour, and I want to thank you. It's been a really nice hour learning about what it's like to be you guys, and it sounds like you have really solved a lot of the problems that are presented when people want to have really device level silicon carbide wafers and gallium nitride, I'll add. And I want to thank you for educating us on some of the issues. And I know that some of the stuff is, or a lot of the stuff is proprietary. So for those who want to reach out, you'll get a copy of the slides, reach out to Dan and Catherine. I just want to point out that we do have the Semicon West. You can see my my desktop here. This gets you a one-day free pass for those who are in the Bay Area or going to be in the Bay Area, July 9th through 11th. I would recommend that you go on the 10th, which is the Wednesday. Very quickly, for those, we still have a lot of people here. I want to just do a really quick poll. And it's just going to take a minute, so don't worry. If you hold your phone up to the screen, you can take this poll. So hold your phone up and join this poll. I'll give you like a 15 seconds. Don't worry, this won't take very long. All right, we're seeing people join this.
Great.
I figure people who are still here now are, let's just say they're the most interested or they don't have a meeting in the next hour. So, okay. So the first thing I want to see how I get this thing to go forward. There. Okay. So I just want to make sure it's working. What state or country, if you don't live in the US or do you live in, just put it in. We'll see people come up here. Just type it in. People, I think I got a message from somebody in the UK who was being blocked, so they're going to be doing this later. So a bunch of people will watch this later. Okay, we got Europe in the house. Okay, cool. So this is the important question. Okay, now that you know about Axus's silicon carbide wafer technology and preparing these wafers, you want to be contacted for more information. Semi has a policy that we don't share emails, but if you want to be reached out to, go ahead and just put your name in here and we will provide this information. And I want to thank you for joining this webinar. And I hope you learned something. And if you're curious about learning more, or if it's important for you to know more, then go ahead and reach out. All right, sounds like we're done. Okay.
Okay.
Thank you, Dan and Catherine. It's been great working with you for this hour, and good luck on this. And we'll see you at our events.
Yeah, thank you, Paul. Thank you, everyone. I hope you found the information useful. We really appreciate your time.
Okay.